In determining the heat of combustion of foods and fuels, a bomb calorimeter is used. The weighed sample is placed in a rigid steel container and ignited. Because the volume of the container is fixed, the measured heat of combustion, Q sub V, is the same as the change in internal energy. How do we use information on energy values to determine heat changes of related reactions? We will discuss that in our next episode. Meanwhile, let's pause for a short break. Different substances respond differently to application of heat. Water, for example, requires a great amount of heat, 4.18 joules per degree Celsius gram, to raise its temperature by 1 degree Celsius. The same amount of heat applied to an equal mass of mercury could raise its temperature almost 30 times as that of water. Specific heat can be expressed as joules per gram degree. This table lists the specific heats of water and other substances. Why is it more painful to be burned by hot oil than by boiling water? Comparing their specific heats will give us the answer. Our body with a normal temperature of 37 degrees Celsius is about 70% water. Because of the high specific heat of water, our body temperature does not shoot up despite a very large amount of heat released by the digestion of food. The presence of water in the atmosphere also prevents drastic changes in ambient temperature. Water absorbs a great amount of heat from all oxidation processes like decay and combustion. With its large heat capacity, water has a moderating effect on climate in countries like the Philippines. Compare these with countries in the Middle East with very hot daytime temperatures and very cold nights. In the laboratory, we can isolate the system and measure heat exchanges using an apparatus called the calorimeter. In the classroom, we can use a coffee cup calorimeter. Helen Bacho will show us how to construct one. Our calorimeter consists of two nested styrofoam cups with a cover. The stirrer and thermometer are inserted through the cover. The inner cup holds a small beaker or glass bottle where the reactants are mixed. To calibrate the calorimeter, we mix known masses or volumes of hot and cold water. The total volume of hot and cold water to be mixed must not exceed the capacity of the calorimeter. First, pour 25 milliliters of cold water into a small beaker. Place this inside the calorimeter. Take the temperature of cold water. Read also the temperature of the hot water in the beaker. Measure exactly 25 milliliters of the hot water using a pipette. Immediately add this to the cold water in the calorimeter. The more quickly you can do this, the less heat is lost to the surroundings and the more accurate your measurement will be. Avoid spills. Cover the calorimeter. Stir the mixture and note the highest temperature reading. We expect the cold water and the calorimeter to absorb heat. We also assume that there is adequate insulation. Thus, the heat absorbed is only that from the hot water. We can now calculate the heat capacity of the calorimeter. Following the law of conservation of energy, heat absorbed equals heat evolved. Based on this relationship, we can determine the heat capacity of the calorimeter. The mass of cold water, m sub c, and the mass of the hot water, m sub h, are both determined by dividing their volumes by their densities. The density is 1 gram per milliliter. SpHT in the equation stands for the specific heat of water, which is 4.184 joules per gram degree. Note that the heat evolved is denoted by a negative sign. We now know the heat capacity of the calorimeter. We can now use this calibrated calorimeter to measure heat of reaction, or the heat absorbed or evolved by a reacting system. For instance, the neutralization reaction of an acid and a base. We'll do just that with 2 molar HCl and 2 molar NaOH. We immerse both containers in a water bath to bring them to the same temperature. We then measure this initial temperature. Use a burette to measure out exactly 25 milliliters of the acid and the base. Then, add the base to the acid. Stir the solution thoroughly and note the final temperature. This is the highest temperature obtained on mixing. This reaction is exothermic. The heat evolved is absorbed by the calorimeter and the surrounding water molecules in solution. Thus, to calculate the heat of the reaction, we apply the relation heat absorbed equals heat evolved. We can express this relation mathematically using this equation. Delta H sub R is a value of the heat of neutralization of HCl with NaOH. You can compare this with the handbook value of minus 57.36 kilojoules per mole. In your class, you may try other combinations of acids and bases like sodium hydroxide and acetic acid, or ammonium hydroxide and nitric acid, to name a few. What we have measured is the heat of reaction under constant pressure. Change is an everyday event. Things move. Wheels turn. A river flows. Iron rusts. Plants grow. Change takes place all the time, everywhere. Without being aware of it, a housewife may cause a change to take place. A scientist, a science teacher, or a science student may deliberately cause a change to occur in a laboratory. Zinc dropped into a solution of hydrochloric acid produces hydrogen gas. Potassium chromate mixed with lead nitrate results in a yellow precipitate, which is lead chromate. An excess of ammonia added to copper ions results in a blue complex. The acid-base reaction between sodium hydroxide and hydrochloric acid evolves a lot of heat. The evolution of a gas. The formation of a precipitate. A change in color. And evolution of heat tell us that chemical changes are taking place. Behind these visible changes are moving atoms and molecules. To move, they must have energy. Without energy, a given system cannot undergo a change. Energy is defined as the capacity of a system to make change take place. If the particles in a substance were immobile, no energy would be available to effect change. In theory, this would take place at 0 Kelvin. To illustrate the energy changes accompanying chemical reactions, let's consider these two reactants, A, potassium iodide, and B, lead nitrate. Reactants A and B each have their own energy content. The sum of the energy content of A moles of reactant A and B moles of reactant B make up the total internal energy of the reactant molecules. Their total internal energy depends on their bulk properties in their particular state. These are mass, concentration, volume, temperature, and pressure if the substance is a gas. Let's mix the two solutions A and B. The sum of the energy content of C moles of product C and D moles of product D is the total internal energy of these products. It is written down like this. The change in the energy content of the reacting system is a difference between the total energy content of the products and the total energy content of the reactants. If there is no volume change during the reaction, as when only solids and liquids are involved, the heat change, QV, is equal to this change in internal energy. This is the equation for the reaction of lead nitrate and potassium iodide. Reactions involving gases, however, involve a volume change. This means that some pressure volume work is done. Most reactions take place under constant atmospheric pressure. For such reactions, the heat change accompanying them is denoted by QP. We shall introduce a new quantity called enthalpy, or heat content, represented as H, to deal with the systems. For a system at constant pressure, enthalpy is equal to the heat content. During a chemical reaction at constant pressure, the heat exchanged is equal to the change in enthalpy, or heat of reaction, delta H, at constant pressure. The enthalpy for each participating substance refers to the enthalpy of formation. This is the heat change accompanying the formation of 1 mole of a compound from its elements in their respective standard states. The term standard state does not refer to standard temperature and pressure. The standard state of liquids and solids refers to the pure forms. Gases are in their standard state when they are at a pressure of 1 atmosphere. A solution is in its standard state when its concentration is 1 molar. An element is in its standard state when it is in its most stable form at a pressure of 1 atmosphere and 25 degrees Celsius. To better understand changes in enthalpy, let me show you something. I measure the temperature of water before combining it with ammonium nitrate. After mixing them, I will again measure the temperature of the reaction mixture. The sum of the heat content of the products is greater than the sum of the heat content of the reactants. There is a gain in enthalpy, and the heat change is positive. This means heat is absorbed. Let us consider calcium chloride and water. Again, we measure the water temperature before and after mixing. After mixing, the temperature of the surrounding molecules went up. This is the case for exothermic reactions. This means that heat was evolved by the reacting system. chemical change which absorbs heat is called endothermic. The evaporation of alcohol and the melting of ice are examples of energy-absorbing endothermic changes. The condensation of water vapor into water droplets in clouds and later as rain, the burning of fuel, and the digestion of food are other energy-releasing exothermic changes. Meanwhile, let's pause briefly for some reminders. Hi. In our last episode, we discussed energy transformations. Energy changes for systems as simple as substance in a test tube or as complex as the Earth are always governed by the first law of thermodynamics. Today's episode deals with energy changes in matter at the level of atoms and molecules. What happens to energy in a chemical change? Is heat evolved or absorbed? What factors affect heat exchanges? Thermochemistry, the study of heat effects and chemical changes, will help us answer all these. Now that we're all warmed up for today's discussion, let's pause for a short break. Today, we looked at enthalpy changes and enthalpy of formation. The latter is a heat change that accompanies the formation of 1 mole of a compound from its elements. We compared endothermic and exothermic changes. We also talked about specific heat and measured heat of neutralization by calorimetry. In our next episode, we will delve into thermochemical equations and the direction of change. We hope that today's lesson has positively changed your attitude toward learning and teaching thermochemistry. This is your host, Ramon Miranda, saying good day.